All right, guys, we're going to talk about graphing linear inequalities in two variables. Before I even get to that, I wanted to recall something first, and then I'll build on it from there. So let's think back to when we were working on some of this stuff in the very beginning. If I asked you to graph a point, let's just call it x equals 5, and on the number line where we get the 5, we would expect to see an actual point there, right? And so at 5 on the number line, you would get a point. You can just put a dot there. We went a little further and we then asked you to graph an inequality. So instead of saying equals 5, something like, for example, x is greater than or equal to 5. So on the number line, we're still concerned about the 5. And since it's equal to, we make a solid dot. But because it's an inequality, we actually shade. So there's a point plus shading. We've progressed a little further and we talked about graphing the equation of a line. Let's just say in slope-intercept form, y equals mx plus b. When we did that, we got something that looks like this. It was a line. Now what I'm asking you to do is graph not only y equals mx plus b, but include this inequality also. So since I'm looking at all of my y's greater than or equal to mx plus b, this would be equal to right here. That's just a line. But I'm talking about outputs that are greater than or equal to that line. So not only am I going to have that line, I'm also going to have this point, for example, and that point, and that point, and that point, and that point, because all of these are above the line. Instead of me having to go through and put all those points on, much like we had to do here, we're just going to shade. So when I ask you to graph an inequality in two variables, x and y, you're going to have the line and you're going to have some shading. All right, so that's just the basic idea. Let me say this. If I were to say, for example, y is, and in fact, actually, let me go right here. I have an example right here. Let me go, actually, not do that one. Y is greater than or equal to 2x plus 1. I want to know, if I give you a point, is 5, 6 a solution? That means, does 5, 6 fall in this shaded area, whatever it is? I'm not going to graph it yet. I'm just going to find that. That means since I have an x and a y value, let me plug it in and see if it's true. If it's true, then yes, this is in the solution. So if I have y greater than or equal to 2x plus 1, and my y value is 6, my x value is 5, I'm just going to see if this is true. So I have my 6, not doing anything to that. This gives me 10 plus 1. 6 is greater than or equal to 11, but that's not true. So no, 5, 6 is not in the solution. Is not in the solution. So if I plug in an x value and a y value and I get something that is true, then we'll be good. Let me try another one. What about, and I'm going to choose something different. So 2x plus 1, let's just call it negative 5, 10. Just choosing numbers here. So again, let y be greater than or equal to 2x plus 1. That means my y is 10. 2, negative 5 plus 1. Is 10 greater than or equal to, well, this is negative 10 plus 1, which gives me a negative 9. Is 10 greater than or equal to negative 9? Yes, that's true. So I can say that negative 5, 10 is in the solution. And since it's more than just one thing, you might hear the phrase solution set, which is the same, just the set of all the solutions. If I were to look at, and I'm not saying this is exactly y is greater than or equal to 2x plus 1, but if I look at that, any point that I find here would be in that solution set. There are infinitely many of them that I can find, so there's a whole set of solutions, one of which is negative 5 and 10. All right, we'll continue this on the next video.